2023 question number 4. This is actually a bit of a classic, so I'd rank this as being one of the most important past paper questions that you can do for organic synthesis, because we see not one, not two, but 3 really important reactions. So we have the Wittig reaction, we have the Grignard reaction, and we have ozonolysis. It talks us through a couple of those, but really, if you want to be getting top marks on the organic synthesis, I'd probably go in knowing how all 3 of those reactions work. So we'll get to them as they come, but so let's just get started with the few introductory tasks. So which functional groups does vitamin E acetate contain? Tick the correct answers in the answer booklet. So nitrile, well, there's no nitrogen here, so we can ignore that. Alcohol, I've got 3 oxygens, none of them are alcohols. Ester, there we go, there's my ester, so yes. Ketone, you might mistakenly think this is a ketone, obviously it's not though, because it's part of the ester group. Ether, here is my ether group, carbon, oxygen, carbon, so yes. And carboxylic acid, no, there's no carboxylic acid there. So that's a nice easy one to get us started. We've got the ester and we've got the ether. Then it says vitamin E acetate has a molecular formula of CXH52O3, determine X. So you just need to count up the number of carbons in here. So I'll go through it slowly just in case you get confused about this one. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. Okay, so let's go ahead and put 31 in there. Next we have a little bit of light spectroscopy, nothing too taxing here. So you read this bit up here, it talks about probably talks about some toxic product. So this breaks down into a toxic product, and we're given 3 pieces of information. We're given the mass spectrum piece of information, proton NMR, and carbon 13 NMR, and we've got 4 possible identities for the toxic product. And you just need to see for each of these pieces of information, does it agree with this formula or not? So let's just write these out. So the implied hydrogen is there. There are 2 implied hydrogens there, and there's 1 there and 1 there, just so I'm clear. So this is C2H2O. This is also C2H2O. This is C3H6O, and this is C2H2O. So in the mass spectrum of vitamin E acetate, the peak at 165.2 comes from the ion resulting from the loss of the toxic product from the ion that gives the peak at 207. So I get a peak at 207.2, and then I lose the toxic product, and I get another peak at 165.2. So the difference here between these, slightly too difficult for me to do in my head, so 207 minus 165 is going to be 42. So minus 42. That is the loss of the toxic product. So it doesn't really matter what this peak is and what this peak is. The point is that to get from this peak to this peak, I must lose the toxic product, and the toxic product therefore has a mass of 42. So I just decide whether or not these have got a mass of 42 or not. 3 of them are C2H2O, so that's 12 plus 12 plus 2 plus 16, which is 42. So clearly you can see that this has a mass of 42, this has a mass of 42, this has a mass of 42, this does not have a mass of 42. So let's go put those in. So yes, yes, no, yes. Then we have the proton NMR has 1 signal. So you have to decide the hydrogens in these compounds, are they all equivalent, or is there more than one? So here I've got a hydrogen and a hydrogen. So those 2 are different. So no, because that would give me 2 signals. Here I've got these 2. Those are the same. So that would give me 1 signal. So yes. Here I've got the 3 on this methyl, the 3 on this methyl. So all 6 of those are the same. So that would give me 1 signal. And these 2 hydrogens would be equivalent. So those would be the same as well. And then finally, the carbon-13 has two signals. So are there two different types of carbon? This carbon is bonded to hydrogen, this carbon is bonded to oxygen. So, yes. Here, this carbon is bonded to the oxygen, this carbon is not bonded to oxygen. So those are two different ones. Yes. Here, this carbon and this carbon are the same, and it's different to this carbon. So there would be two signals, even though there's an extra carbon compared to the others. These two are equivalent, so that would be okay. And then these two carbons here, well, those two are the same. So no, that's not going to work. So there you can see the toxic product is this one, okay, because that's the only one that agrees with all three pieces of information that we've been given. Okay, so that's the nice warm-up done, and then we move into our synthesis of vitamin E acetate with the Wittig reaction. Okay, so like I said, in this question, this is one where they really hold your hand and walk you through it. I wouldn't anticipate that they would approach this reaction like this again in future. In other words, if a Wittig reaction were to come up in future, it's unlikely that they're going to give you all this hand holding that you see in this question. So how do they hold your hand? Well, they give you the generalized reaction scheme. So it's an aldehyde and the phosphonium ylide, giving you the two possible stereoisomers of the alkene and then the other product, which we're not going to be interested in. So really important to understand what's happening here. So this carbon becomes this carbon. So the carbonyl carbon. And then the other molecule, the carbon bonded to the phosphorus, is this carbon. So this is a carbon-carbon double bond forming reaction. One carbon from the carbonyl, one carbon from this phosphonium ylide. And then you're given one other piece of information, which is that if there is a carbonyl or a carbon-carbon double bond adjacent to the negatively charged carbon in the phosphonium ylide, then you get the E isomer. Okay, now if you want, for this question, I think it is okay just to, when you see E isomer, look at this and just think trans. Alright, now there is technically a difference, but for E's, we're just going to say that for the E alkene, they're both on different sides. The Z alkene, they're on the same side. So, they give you this. Then, they go one step further and they give you two more examples. Okay? And, you know, they really want you to be able to understand how this reaction is working. At this point, if it's still not quite clicking, one thing I always recommend is to count the carbons so you understand what's happening. So, I mean, firstly, you want to be able to identify the two important carbons. So the important carbons are going to be this carbon and this carbon. So can I identify those carbons in my reactants? So that carbon becomes that carbon, and then this carbon here becomes this carbon. And I can check that I have enough carbon. So 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, and I've got 1, 2, 3, 4, 5, 6, 7, 8, 9. Because one of the mistakes that we quite often see in these organic synthesis questions is just a lack of conservation of carbon numbers or atom numbers, that you just people sort of they forget to count a carbon, so they'll bond it directly to number 6 and they'll forget number 5. So counting the number of carbons in the reactants and counting the number of carbons in the products is generally a safe way to go, to double check you've got the right answer. Then you're given a second example where you've got now you've got this carbonyl adjacent to the negative carbon, so it gives you the E isomer, or this trans format. Okay, so by this point they've given you tons of information. They've given you the generalized reaction with R1 and R2. They've given you an example with a Z isomer, an example with an E isomer, and then they say, okay, your turn, you go ahead. So what we're going to do is we're going to bond the carbonyl carbon with the negative carbon in the phosphonium ylide. So we can worry about stereoisomerism later. First of all, I just need to get it drawn out. So this carbon here is this carbon here, and then it bonds to this carbon. And that is bonded to one other. So the double bond, you can see this carbon here is this carbon, and then this carbon is the one that I've marked in red, and then that is the double bond. Okay. Now, because of the ring here, there is no need to worry about cis-trans isomerism, and likewise, there's no carbon-carbon double bond or carbon-oxygen double bond here for me to worry about. Okay. Now, actually, let's just do one last check. I've got 1, 2, 3, 4, 5, 6, 7, 8 carbons. In my product, do I have 1, 2, 3, 4, 5, 6, 7, 8 carbons? Yes, I do. Okay, we're good to go. Now the next one, I'm going to bond this carbon to this carbon, but I've got this double bond here, which is adjacent to my negative carbon, which means that my product needs to be the E isomer. Okay, so let's just go ahead. I'm going to draw this one out. I'm going to draw it in the corner because when I do these, I don't know which way it's going to go or how much space it's going to take up, so I need to be a little bit careful. In the test yourself, you'd probably want to do it on a separate piece of paper, or in the answer in the question booklet. Oh, this is the question booklet. Fantastic! I can just draw it in afterwards. So there, that carbon is that carbon. Okay, and that carbon is bonded to that carbon. I'm going to go up here. So that's my double bond. So this carbon is now this carbon, and then it's trans, or it's the E isomer, and then I've got this double bond, single, double, and then 2 singles. Okay, now it does look a little bit different from what you see in the answer booklet, but it doesn't matter because all 3 of these are in the E configuration. So I could rotate around this one here and get it a little bit more neat. In fact, I'll just show you that now. So this one here we've already established is that, and then the sort of the neater way of drawing this would be so I've just flipped it around, and then I get like that. But it doesn't matter, either way would be acceptable. And then finally, just to make sure, and they really do like to do this, they've done this in lots of other questions. I remember off the top of my head that a Diels-Alder question they had where they give you 2, which are the forward, and then they give you the third one, which is the product, and ask you to work backwards. So I've got 2 double bonds. So there are 2 ways of doing it. So let's start with making this double bond first. Okay, so it's obviously going to be that. Okay, and so this carbon is this carbon, this carbon is this carbon, so my phosphonium ylide is going to start here. Okay, and this is where it's really easy to get to lose a carbon. So then I have my PH3P, and now I just need to carefully track all of my carbons. So that's the carbon of the double bond, that's that carbon, then I've got the double bond, and then I come up and I have it like that. So just double check everything else makes sense. So this is the E isomer, and I've got a double bond next to my negative carbon, so that makes sense. And then I've got 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. Okay, fine. So second option is we make this one. So now this is going to be my carbonyl here. So I'm going to have that is my aldehyde, and then this carbon is going to be my negative, and then that's bonded to the PH3P. Okay, So let's just double check. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. It all adds up. Okay, so that was part of that was basically all the training. So the training that you receive now is generalized, illustrative examples, a couple of exercises to get you warmed up. Should I write those? I'm not going to bother writing them in there. That's fine. And then now we go into the synthetic route, the main part of the question. Okay, and obviously you should be expecting to see some Wittig reaction action in this question. So we've got the synthesis of vitamin E acetate, all the way down here at the bottom of the page. Okay, and we're going to start up here with this acetic anhydride addition to some sort of aromatic compound. So what this is going to do is it's basically going to form these esters. Okay, so this ester here is going to be formed from the reaction of an alcohol onto here. Okay, so it's going to be sort of like just a bit hand wavy. That's going to go on, go up, come down, and come off. All right, just as a very sort of quick way of understanding it. But the important thing is it's going to be an alcohol group, which is great because this has got 3 oxygens in, and those 3 oxygens are going to be from the aldehyde, because nothing's going to happen to the aldehyde, and then this is going to be an alcohol, and this is going to be an alcohol to start with. So let's just go in straight away and draw that out. So I can have them side by side, and you'll see how this works. So I've got my benzene ring in the middle with my 3 methyl groups, the aldehyde, which doesn't do anything, and then alcohol, and then I just need to double check that I've got enough carbons. So I've got the 6 in the ring, 7, 8, 9, 10, so that's C10. H, well, I've got 3, 6, 9, 10, 11, 12, H12, and I've got my 3 oxygens as mentioned before. So I get my formula, which matches my formula for A. So we're done. Okay. Then, well, we've got the reaction that we just practiced. So obviously it is going to add to the aldehyde. It does say in the preamble for the Wittig reaction, where you had all the information about the Wittig reaction, that in this reaction an aldehyde or ketone. Don't get confused, this is not a ketone, this is an ester, so this is not going to react, only this aldehyde here is going to react. And obviously what's going to happen is this carbon is going to bond to this carbon, making a double bond. So let's go ahead, draw it in. So I've now made these ester groups in the previous step, and then here we go, I get that carbon double bonded to that carbon, and then that is the rest of that group. And importantly, I've got the carbonyl adjacent to the negative carbon, which means that my double bond has to be this trans or E isomer. Okay, done. Then we have reduction, H2. Okay, now the reduction is basically just going to reduce double bonds. It's not going to reduce the benzene ring, it's not going to reduce the carbonyl, it's just going to reduce this double bond here, quite simply. So that one doesn't require too much thought. Like that, and then I just have my bit like that. Okay, so one left, D. And this is where this question gets a little bit wild. Just out of nowhere, you get this MgBr coming at you. So this is the aforementioned Grignard reaction. just trying to think off the top of my head if they've done a sort of a situation like this where they taught you through a Grignard process. Doesn't, off the top of my head, I can't think of one, but by this stage, I think it's pretty much accepted that you will be able to identify the organomagnesium or the organolithium reagent and know that it's going to be a carbon-carbon bond forming reaction. So the Grignard reagent is going to react at our carbonyl centers. 1, 2, 3. Okay, so that's where it's going to form these carbon-carbon bonds. But wildly, we have 5 equivalents of it. And we get D, which is the thing that we want, which is going to have this. This is the one of them. One of the equivalents is here in my target molecule. The other 4 of my 5 equivalents end up here. So I get 2 equivalents of this compound, which has got 2 of the original Grignard reagents in. So 2 in one molecule, 2 molecules, so 4 equivalents are in here. So 1 is going to go into the final product, 4 go in here. And that's because Grignard reagents do this successive addition to ketones. Okay, so let's think about it. The easiest thing for us to do is to probably go ahead and draw our basic outline. I know that nothing's going to happen to my benzene ring. I know nothing's going to happen to these methyl groups. The esters I'm going to leave for the moment. Then I'm going to come in and I'm going to draw this out. Okay. Now, what's going to happen is I'm going to have that carbon is just that carbon there, and then I'm going to add on my 1 equivalent, and it forms the tertiary alcohol. Okay, so that's what's happening there. At this point, we can just look at the molecular formula. So we have C15H20O3. So I've got 6 in my ring carbons, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, fine. And I've got 3, 6, 9 hydrogens, 10, 11, 12, 13, 14, 15, 16, 17, 18. So I'm missing 2, but I didn't count these. So I can just go in and put OH there, and now I've got my 20 hydrogens and I've got my 3 oxygens. Okay, so that's fine. But I am going to do a little aside to work out how we get this funny thing here. All right. So what I've got is, if I take this here, and I'm just going to draw out a section of it. Okay, so I'm not going to be super strict with my my mechanism here. You have to forgive me. I've mentioned before I'm not an organic chemistry specialist. So if you are, don't get upset. You were warned. So what's happening is this carbon here is bonded to this carbon. So it comes in, goes up, down, and then kicks that out. All right. So what do I end up with? I end up with I've still got my carbonyl. I've got my carbon here, and now I've attached this to it. Okay. So my ester has become a ketone. But then another equivalent, and this is why you have to add in 5 equivalents, because this reaction will happen, and then one of the other equivalents will just get used up by doing this. So this comes in like that, goes up, and you get the tertiary alcohol. So you get the OH, the original carbon, that's that carbon there, this one that I added first, and then this one that I've just added. Okay, and this just consumes your Grignard reagent, which is why if you want to get the one that you actually want, you have to add in the extra equivalents. Okay, so that's where it goes. All right, now that, I mean, I think when people first see this, if you've got no idea about Grignard reagents and successive additions, this just looks a bit wild. So that's what's happening. Again, that's quite complicated. If you need to, I'd go back, have another little look at that. Then, upon the addition of hydrochloric acid, D, reacts intramolecularly, obviously, because I've got a ring here, okay, to form a ring and a molecule of water. This reaction occurs via an intermediate tertiary carbocation. Okay, fine. So, here, I need an intermediate tertiary carbocation. Alright, so I've got 1, 2, 3, 4, 5 carbons, and then I've got my 6th oxygen. So that's going to be, again, look, let's look in the product here. I've got 1, 2, 3, 4, 5, 6 in my ring, and here I've got, count it, I've got 1, 2, 3, 4, 5, and then this oxygen is going to be the 6th. Okay, so how do I get my tertiary carbocation? The tertiary carbocation is going to be at this carbon here. So it's going to be, just really, you've got to be so careful every time you draw it out. Make sure you're drawing it out properly. Any slight mistake here will be penalised at least once. Probably not more than once, but you know, if you drop a carbon somewhere here, you're going to get punished for it. So then we go up, up, and then we can just have that and that. And then that is my carbocation. And then this oxygen will come round and form the ring to there. Okay, so on to the final part of the question. We have the second part of the synthesis. And we need to know W, X, Y, and Z. Okay? So, number 1, W. Hydrogen, reduction, Lindlar's catalyst. This one's a tricky one. If you don't know what Lindlar's catalyst is, obviously hydrogen's going to be a reduction. So you've got two options. It's going to be either the alkyne to the alkene or the alkyne to the alkane. Now, at this point, if you know that Lindlar's catalyst gives you selective reduction to the alkene, fantastic. And that's what it does do. Okay, so I'm just going to go in and I'm going to just write that out. So make sure everything is correct. Just have that kicking off there at the side. Now you might be saying, well, hold on, there's just no way. How would I know that Lindlar's catalyst does selective reduction to the alkene? That's a reasonable position to be in. But down here, you are given this piece of information. The reaction which transforms W into X and byproduct Y is called ozonolysis. The general reaction scheme for ozonolysis using ozone and zinc is shown below. So this is the second general reaction scheme they're giving you in this same question. Now, I do know for definite that ozonolysis has come up just as a step by itself without any information about the ozonolysis reaction post this question appearing in 2023. So here in 2023, they've given you the general scheme for ozonolysis. In subsequent years, they've just given you this, and they said, well, look, maybe you should know what ozonolysis is by now. So I'm not saying they'll never show you the general reaction again. I'm just saying that they have in the past taken it as given that you would know it. But I'm getting ahead of myself. Why is this important for this first step? And the reason it's important is because in order for the ozonolysis to happen, I need a carbon-carbon double bond. So the fact that I need a carbon-carbon double bond gives you that hint that Lindlar's catalyst is going to selectively reduce to the alkene rather than reduce all the way to the alkane. Because if I reduce all the way to the alkane, I cannot do this ozonolysis reaction. Okay? And I know that the ozonolysis reaction must be happening at this end of the molecule because nothing is changing. Nothing is changing about the other part of the molecule. Okay, if you look to the left of both my hands, okay, so this bit here and this bit here, They're identical. Nothing else is happening. So I'm focusing everything down here, which means that this must be an alkene. Then I do my ozonolysis to get X. So nothing changes over here. But this carbon-carbon double bond then becomes carbonyl, like that. Okay, so that is my product X. The byproduct Y, well, this carbon here, that I'm pointing at now, this carbon here, and this carbon here, these are the same carbons. So when I did my ozonolysis, I broke this double bond. One carbon stayed here. The other carbon goes onto the other product. Okay, like here. Okay, and what's this carbon bonded to? It's bonded to 2 hydrogens. So I get my carbon with my double bond oxygen, and I get my 2 hydrogens. Okay, so that's my byproduct Y. And then finally, really fantastic question. You know, they've really outdone themselves, because the very last part, it is, what do I need to add to this to get this? And it is a carbonyl to a carbon-carbon double bond, which means that it is, you guessed it, one final Wittig reaction. So this carbon here is this carbon. Really, I cannot stress enough, I know I keep going on about it, but always just try and identify which carbon is which carbon, otherwise you're just going to get completely lost. And then this carbon here is going to be the first carbon in my Wittig reagent. So it's going to be, let's try and keep it neat. Yeah, in fact, this is going to be a little bit. It's going to be a bit messy. I want it to look like that. Okay, so this carbon is my. Let's just do it like this. That's my negative, and then I can put it down here. PH3 like that. Okay. So this carbon is this carbon, and then I've got this one, this one, this one, and then I just draw in the rest of the chain. So, whoops, down, like that. Okay, oof, that looks almost as bad as some of the structures I see my students draw, but I'll take it for now. And there you have it. There is your second, or your third, or your fifth, I can't remember now, Wittig step. Okay, again, it's a tricky one, but if you pause it, go back, do it again, you should be able to follow it all the way through, and then you don't have to worry that the final step is then the second reduction to get the alkane. So, just finally, before I go, Wittig, Grignard, ozonolysis. I would put those down as the things that I would recommend just having a familiarity with. So, you know, just be aware. Wittig, Grignard, ozonolysis, all worth knowing. There are a few others, but I'll like enols just seems to be coming up again and again and again. But if you've done more recent past papers, you'll have seen loads of that. But yeah, all stuff worth knowing.